Hello, so today we're going to be solving this initial value problem using the power series, which indicates that we're going to use the Frobenius theorem with all the sums, and make sure to format your final answer as an elementary function. So that's going to our final answer is going to boil down to a polynomial equation, or sine of x or cosine of x or something like that. And it's not going to be like x squared plus x cubed plus dot 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 dot. It's just going to be a singular polynomial. Oops, sorry, copied that. And then we're also going to assume that our solution is about the ordinary point. X equals 0. And then our first step is to plug in the initial values given so that we can find C of 1 and C0 to plug in the coefficients later on. So y equals C0 plus C1x plus C2x squared plus dot dot dot. So this is what we're trying to find in the end. We're trying to find y. So in the end, when we find all the coefficients using the power series method, we're going to plug them back into y. So we're given that y of 0 equals 9. And when you plug in 0 for all the x's, they all cancel out. So you get C0 equals 9. And then y prime equals, and so C0 is going to go away. And so then you have C1 plus C2x plus 3C3x squared plus dot dot dot. And so when you plug in 0 into x, because y of 0 equals 0, all of these are going to cancel out. And so then C1 equals 0. So we're going to box these to keep these in mind for later on. And our second step is to write out all the series that y equals and y prime equals and y double prime equals. So y equals sum of infinity starting at n equals 0, cn x to the n. And then you take the derivative of that, you're going to get sum of infinity. And when this starts at n equals 1, because when you take the derivative, the x is going to be n to the power x to the n minus 1. And so you want to compensate for this being n minus 1 by doing n equals 1 for the starting point of the sum. And then I think that's the reason. Hopefully that's correct reasoning, but yeah. And then y double prime equals n equals 2 to infinity, goes to infinity. And when you take the derivative of y prime, you get cn times n minus 1, and then x to the n minus 2. So yeah. Now that we have these written out, we can plug y prime, and y double prime back into our original differential equation. So we're going to get sum infinity x equals 2, cn n minus 1, and then x n minus 2 minus 2x, sum of n equals 1, cn n minus 1, plus 8 n equals 0, and cn x to the power of n equals 0. So now we're gonna distribute all the coefficients that we have for the sums. So if you move this here, then it becomes x to the power of n, and then this is just a integer. So you're gonna write that out. So I'm just gonna copy paste this. Oops. because this doesn't change. This doesn't have a coefficient. And then this part becomes sum n equals 1 to cn n, and then x to the power of n, plus this doesn't really change, so I'm just going to copy paste this. You just move the 8 inside. So now we want to make all the powers of x's, like x to the n and x to the n minus 2, we want all of them to be the same. So we're going to change this power to be x to the n. We want it to be x to the n. And how we're going to do that, so this is our third step, combine same x to the power, same x powers. And so this first series we have here, where the starting point is n equals 2, is actually I'm just going to copy paste here so that we know what we're doing. Oops. So then we're going to say that k equals n minus 2. So then n equals k plus 2. Because we want it to become x to the n. So then n equals 2 when k equals 0. So you plug in k equals 0, then you get n equals 2 here. And then the other ones, we just have n equals k and then n equals k. Just gonna write some lines. There you go. And then because of this, k equals 0 when n equals 2, the starting point also changes for the sum. So then it becomes sum of k equals 0, ck plus 2, because n equals k plus 2, so we plug in k plus 2 for n into the sum, and so this becomes k plus 2 times k plus 2 minus 1 times k x to the k, because n minus 2 equals k for this first sum here. And then for the second sum, we're just going to plug in n equals k. So all the n's here change into a k, because that's what we wrote down for here and here. So we're going to do that for the second and third sum. So I'm just going to copy paste these sums and then change all the n's. Change all the n's to k's, because copy pasting is just easier. So then this becomes k equals 1, and then this becomes, these are all k's. So now that we have x to the k's for all three sums, I'm gonna make a page. For all three sums, we can now factor out the x to the k. So also normally, I think in lecture we learned that we should change the starting points to be all the same. But how I'm gonna avoid doing that is just k equals 1 for all the for all the sums, and then we're just gonna ignore the k equals 1. Yeah, and then we're gonna factor out the C2 and C naught, or C0. So step 4 is that we're gonna plug in all, actually, sorry, we're not gonna ignore the k equals 1. So what we're gonna do is that we're gonna plug all the starting points of the sums into the sums. So we're going to plug in k equals 0 for all the k's, and we're going to plug k equals 1 into all the k's, and plug all of the, all of that. And then what we're going to get is, so once you do that, you get, so C of C2 times 2 times, this is just 1 times x to the 0. So that's just 1. And then, so you plug in k equals 1 to there, you get C of C1, 2C1 times 1 to the x power 1 plus, plug in 0 there, x to the 0, and that's just 1. So then I'm just gonna condense this all into one thing. C2. Oh wait, actually, sorry, I'm looking at my solutions right now, and we're just gonna plug in k equals 0. Sorry, plug all starting points of the sums with starting points of, starting points of k equals 0 sums. So for all the sums that have k equals 0, we're going to plug in k equals 0. So then we can get C2 and C0 for the coefficients. So we're going to leave the k equals 1 alone for now. And then we're going to factor out the x to the k. Yes, that's what we're going to do. Okay, so we're going to delete this part about plugging in k equals 1. So then you just have that. And that's just for the k equals 0 sums. K equals 0 sums. I don't think I'm using proper terminology, but it's okay. Okay. And then we're gonna add k equals 1. And then we're gonna factor out the x to the k. So then it becomes k plus 2 times k plus 1. And that's ck plus 2. I forgot about that. And then minus 2 kck plus 8ck. And then you factor out the x to the k for all the sums. And you plug in k equals k equals 0 for all the sums that, start at k equals 0 to get 2c2 plus 8c naught plus the sum we just created here when we factored out x to the k. Hopefully that makes sense, but yeah. So to recap, we plugged in k equals 0 into the sums that have k equals 0, and then we factored out x to the k for all the sums. So now we have this. And then, so this, I think it makes the sum valid for k equals k is more than or equal to 1. So you can't have it, so you can't have k is less than or equal to 1. And then we're going to solve for the higher c. So c of k plus 2. So if you see all these c's, so this is like 2, but in the sums you have k plus 2 and then k and k. So we're going to solve for k plus c of k plus 2. So our fifth step is going to be, actually we're going to plug in c2 equals 8c naught, because we already found c naught over here. So c naught equals 9. So 2c2 equals negative 8 times 9. So then c2 equals negative 36. So we're going to keep that in mind as well. So then our fifth step is that we're going to solve for the higher c. And the higher c is ck plus 2. Does that look like a k? I'm sorry. My handwriting is really bad. So yeah. So because this whole thing equals to 0, we're going to set everything in the sum of k equals 1 to 0. Hopefully that makes sense. Because x of k can't equal 0. So this whole thing in the sum is going to equal 0. Okay, and then we're going to isolate c of k plus 2. So c of k plus 2 equals, we're just going to factor out the ck here, and that's going to become ck minus 8. And then you take this whole thing, and you divide it, you move it over to the right side, k plus 1. Now, what we're going to do is our sixth step. So our sixth step is that we want to find all these coefficients for, y equals c plus c naught x, blah, blah, blah. So to do that, we're just going to plug in different k values until we find a pattern. And also keep in mind that over here, because our sum starts at k equals 0, that k has to be, when we plug in k values to find the coefficients, it has to be more than 1. So I'm just going to write down that plug in values of k is more than 1. And then we're going to find a pattern. Can you read that? I'm not sure. Pattern, I think, yeah, pattern of coefficients. To find y. This is going to be a very large file. Sorry about that. So we're going to start off k equals 1. So c of 3 equals c1 times negative 6. And then because c1 equals 0, then this whole thing equals 0. And then we're going to plug in k equals 2. And so then so this is k plus 2. So that's going to be c of 4. And that becomes c2 times negative 4 over 3 times 4 equals negative 4 times negative 36. Does that look like a 3? I'm very self-conscious about my handwriting. And that equals 12. And we're going to plug in k equals 3. So we haven't really found a pattern yet. So we're just going to keep going. C3 times negative 2 over 5 times 4. And then because C3 equals 0, that just equals 0. And then next we're going to plug in k equals 4. Well, you can see that, but k equals, oops. So that equals C6. C4 times 0 equals 0. As you can see, we already have like a pattern of 0 going on, because as you keep going, it's just going to become C7 equals C5 times 0, and then C5 is 0, so then it's just going to keep equaling 0. So that's where our series kind of stops. So we're just going to say that it equals 0, and then if you keep going, it's just going to equal 0. So we're going to stop there. And so finally, we found a pattern, and our pattern is that it stops at C4. So then our polynomial is going to stop at C4 for y equals whatever polynomial we have. So our general solution is going to be y of x equals C1 plus C2 x squared plus C3x cubed plus C4 x fourth. And so if we plug in all the coefficients we found, we have 9 minus 36x squared plus 12x to the fourth. I got a little bit confused in the middle, but hopefully that all makes sense. And yeah. Sorry if it was a bit messy.